Hey everybody, it's Tuesday, November 17th, if you can believe that. And as you can see here in the aim today, our goal for today is to discuss inclined planes. Really, by taking Newton's laws and analyzing the motion of an object on an inclined plane. So, really, what we're going to try to do in this single video is go through the entire thing. Talk all about an inclined plane, talk about the entire variety of problems that you could see about an inclined plane. I think we're going to take this in a fairly straightforward and logical order, but essentially what I'm going to try to do is get as far as we possibly can in the video here today. And so what I hope you realize going into this is that because the aim says how can we use Newton's laws to describe the motion of an object on an inclined plane, basically every single thing that we're going to be doing today is in some sense building on the things that we discussed previously in the other videos. And so it makes no sense to do anything else other than to just get right into it by asking a question. So the first question here that we want to ask is how can we describe the causes for the motion of an object that is resting on an inclined plane? So if an object is sitting on an inclined plane, what's going to make it start to move? And a lot of people give an answer that's usually slightly off, because a lot of people usually give an answer that basically says, well, gravity is what makes it move. Not exactly. Because notice, first of all, gravity is acting on the object right now. And gravity is acting in a direction that is straight down. And when I hit start on the simulator here, the object does not move. Now you could make an argument, well, it's not really an inclined plane yet because there is no incline. Okay, fine. Then let's make the angle 10. So now it's an inclined plane. And when I hit start, you're going to notice this thing begins to move. But as I mentioned a moment ago, the force of gravity acts straight down. And the object is not moving straight down. The object is moving that way. And so it's important here to be very precise about the way that we are making this argument. Now, it is true that the actual weight of the object acts straight down. But what we can see here is that part of the weight does act down the incline. And so notice here, even though this vector is straight down, we can say that part of it acts in a direction down the incline, which we can see more and more as we continue to raise the angle. Now, these arrows are not going to apply anymore, of course, but as you can see now, as we lift the angle, more and more of the weight is directed down the incline. And we can tell that it is, in fact, the part of the weight that's directed down the incline that is making this thing accelerate. Because if we increase the angle and we make it and we allow it to begin, you can see that the acceleration of this thing gets larger and larger and larger the more and more we lift up the angle. And so notice in 2.74 seconds, this thing made it 21 meters. But if I put it over here, by the time 2 seconds goes by, you're going to see it's barely going to have gone anywhere. And so notice now we're already into 3 seconds almost right now, and it's not even gone 10 meters yet. And so the idea here is that the angle being lifted higher and higher and higher means that this thing is going to have a larger and larger acceleration. Obviously, the acceleration is just listed right there, but that's the basic idea. That part of the weight is directed down the incline, and that when the object moves down an inclined plane, it's accelerating due to the portion of the weight that's acting down the incline. Take a second to pause this video here and write that down, and when you hit play, we'll move on. So what we want to do here, as is the case for all these Newton's laws problems, is we want to draw a free body diagram, a diagram of the forces that are acting on this object. And so the first thing we're going to do here is we'll just write the heading free body diagram, and we'll just draw a generic diagram here. Now, what we want to do when we're drawing this free body diagram is we actually want to draw the object on a ramp, because I think that makes it a little easier to follow. And so we'll draw the diagram on the ramp. And so the way that I do this is I draw my ramp, and you could just ignore that bit at the end. And then what I like to do is I like to draw the object as a box. But of course, because all the free body diagrams usually have a dot placed at the center of the location of the object, I then draw a dot at the center of the box. And so there's our dot at the center of the box. Now, of course, I couldn't erase that end without erasing that whole bottom line. And so I'll just redraw that, and then we're off to the races here. Now, the first thing that we should note is that the force of gravity always, always, always acts toward the center of the Earth. And so we're going to have the force of gravity coming straight down. And really, one of the first things that we want to pay attention to here is that the normal force, and this is really true for the first time ever, the normal force is not going to be exactly opposite of the force of gravity, because the normal force is defined as always being perpendicular to the surface. And now that the whole surface is tilted, the normal force is tilted too, because the normal force is supposed to be parallel to the surface. Now, this is true. This diagram will look like this if there is no friction. However, if there is friction, it should be clear to everybody the direction of that force of friction. Because if it's static friction, then it's acting in the opposite direction of the force that's trying to make the object move. And if it's moving, then it's acting opposite the direction of motion. And it should be clear to everybody that the force that's trying to make this thing move is moving down the ramp. And so that means the force of friction is going to be up the ramp, like this. And that's a friction force, and so it gets the subscript F. And so we want to say a couple of things about the directions of these forces before we move on. The first thing we're going to say about the force of friction is that this should be parallel to the surface. Of course, then we'll also say the normal force is perpendicular to the surface. And we'll say here that the gravitational force acts straight down. And so our forces are going to look like this. Now, you should notice here is that we have a little bit of a problem. And the problem that we have is that when we use a traditional coordinate axis with the positive x going in one direction and the positive y going in a direction perpendicular to that, like showing you horizontal and vertical, it should be clear that while the force of gravity is acting straight down and really is acting purely in the negative y direction, the normal force is not acting perfectly along the y-axis. It's acting at an angle relative to the y-axis, and the friction force is not acting along the positive x-axis. It's acting along the surface, and so really only part of it is acting along the x-axis, or really we would have to break it into components like we would have to for the normal force. And so we have a little bit of an issue on our hands, which is that we have a problem where we have three forces involved, and two of them do not act along the axis. Now, this problem is further magnified when we take a look at the components. And so this is not going to be an official free body diagram, but rather is going to be a component diagram. Now, what we could do, to be clear, what we could do, if you really wanted to, is break up the normal force into two components, one that goes purely in the positive y direction, and then purely in the negative x direction, because it would be pointing this way towards the left of the screen. And we could do the same thing for the force of friction. We could find a component that purely acts in the positive x direction and one that acts purely up. But rather than take the two forces that don't act on the y-axis or the x-axis and break those into components, we could just break the force of gravity into components. Because if you notice, and we'll have to go ahead and draw this diagram again, if you notice, we have the normal force being totally perpendicular to the surface, and the force of friction being totally parallel to the surface. And while the weight acts straight down, we can say the two components form a right triangle if we draw them like this, where that one would be FGY. Notice you just basically extend that line down from the normal force, and then the other component, FGX, would act like this. Notice, parallel to the ramp. And now we only have to break one force, FGX and FGY, into components, and now all of our components, or at least the components that matter, FG is off at an angle, but if we have the components of FG, then that doesn't really matter, are now either parallel or perpendicular to the surface. And so essentially what we do is we start with a situation like this, where the surface is flat, and we have our plus x plus y axis. And now since we rotate the surface like this, we're just going to take our coordinate axis system and rotate it like that also. And so essentially, instead of having our x and y axis like this, we're just going to take it and rotate it and put it like that. Let's write that down in a note. Now that all vectors or components are either parallel or perpendicular to the surface of the ramp being the most important part here, we'll simply rotate our coordinate system so that the x-axis is parallel to the ramp and the y-axis is perpendicular to the ramp, where the plus y axis points up from the surface and the plus x-axis points down the ramp. And so that means if our ramp looks like this, then our coordinate system is going to look like that, where that will be plus x, and that will be plus y. And if we do it like this, then our axes will look like that. It doesn't really matter, just as long as we're being consistent. Take a second to pause this video here and write that down. And when you hit play, we'll take a look at this diagram in a little more detail. Now I'm going to try to draw this one really carefully so you can see it. If we take our ramp and we draw it, what we have now is a situation that looks like this. And so I'm going to have my box, and I'm going to say here, this is at an angle theta, and we're going to have the weight coming straight down. We're going to have our normal force coming up at an angle like this. Just ignore that. And then our force of friction being parallel to the surface, where x and y axes then are going to look like this. Basically like that, parallel though, of course, where that'll be plus y and that'll be plus x. And so notice here, it is true that the normal force and the friction force act completely along those axes. The friction force acting in the negative x direction, the normal force acting in the positive y direction. The weight is the only force that doesn't act in either direction. And so what we're going to do here is we're going to recognize one key fact. And this key fact that we're going to recognize here is that we can break that weight up into two components which are parallel or perpendicular to the surface. And so I'm going to have my weight coming straight down, my normal force perpendicular to the surface, and these are not drawn to scale, by the way, my friction force going parallel to the surface, and I'm going to have my components here like that. And so notice here that this would be what we're going to call FGY, and this is what we're going to call FGX. Now, it may seem like we have a little bit of a problem on our hands, though, because it will be the case that this angle, the angle the ramp is tilted at, is given in the problem. But we don't know any of those angles in the triangle. But of course, because you're all math wizards, it should be fairly clear what that angle is if we do a little bit of trig, a little bit of geometry. So the first thing I'm going to say is if this angle, like let's just say, of course, that's a right angle. Let's just say this angle is 30. If this angle theta is 30, that means this angle is 60, right? Because they all got to add up to 180. So let's say this angle is 90 degrees minus theta, right? And so now, looking at this diagram here, notice what we have in red. It's an alternate interior. Tilt your head and look to the side. It's that classic Z. And so that means this angle, 90 minus theta, is this angle in the triangle. Notice this angle in the triangle is a right angle. And so that means if this angle, 90 minus theta, is the same as this angle in the triangle, 90 minus theta, and this angle is the right angle, like that one, then this angle here, theta, has got to be equal to that angle. So inside of our vector triangle here, where FGY comes straight down, FGX comes over like this, and notice I'm just rotating it to make it easy to see from this angle. FGX comes like this, and FG comes straight down. That's our angle. The same as the angle the ramp is tilted to. And that makes finding our components a heck of a lot easier, because we can find our components by just doing some simple trig. And so the first thing I'm going to do is I'm going to draw this kind of like it's shown on the ramp. So that would be FGY. This would be FGX. That's the angle theta. And of course, this gets a lot easier to see if you rotate it and have FGY coming straight down, FGX coming over like this, and then FG being the hypotenuse of the triangle. Of course, that should be drawn straight. Please forgive me, it is difficult to draw on this stylus pad on the computer. And the angle like that. So the key difference here between this vector triangle and every one we've looked at so far is that this angle is being measured from the vertical. So if we talk about trying to solve for FGY, notice FGY is the adjacent side of the triangle, and FG is the hypotenuse. So that means if we apply the cosine of the angle, we'll get the adjacent side over the hypotenuse, right? That's what SOHCAHTOA says. So when we apply that to this triangle, we'll get the adjacent side, FGY, over the hypotenuse, FG. And that means when we solve for FGY by multiplying both sides by FG, you get FGY equals FG cosine theta. Or, if you want to be super precise about it, of course, depending on what you're given, you get FGY equals mg cosine theta. Similarly, for FGX, we see that when you do this for FGX, now that component, FGX, is the opposite side of the triangle from that angle. And so when we take the sine of the angle, we have sine theta equals the opposite side over the adjacent side, of course. And so that gives us sine theta is equal to the opposite side, FGX, over the hypotenuse, FG. And so when we solve that for FGX, we get FGX equals FG sine theta. Or if we want to be more particular, FGX equals mg sine theta. And now we can solve it whether we're given the mass or the weight. What's different about this, again, is that when you have any other vector triangle like we've had so far this year, the angle is given as the angle between the x-axis and the vector. But because of the arrangement of the inclined plane, the angle in that vector triangle, the vector triangle that was shown here, happens to be the vertical angle in the triangle, not the angle from the horizontal. And so because we're dealing with the vertical angle, the sine and the cosine switch. And so this would be a super important note for us to write down. And so we'll say here, note, usually when solving for vector components, we are given the angle measured from the horizontal. However, for an inclined plane, the angle at which the ramp is tilted is the vertical angle, I should say is equal to the vertical angle in the triangle. This means that the sine and the cosine switch in the component equations for an inclined plane. And I'm going to write in parentheses here, usually sine goes with y and cosine goes with x, but here sine goes with x and cosine goes with y. This is super important. So take a second to pause this video here and write that down. And when you hit play, we'll take a look at how we can actually use this stuff to solve problems. So another way of looking at the free body diagram for an inclined plane could be a little something like this. Now, this isn't drawn to scale, so we're not going to go too nuts about this here, but the idea is the normal force is acting perpendicular to the surface. The friction force is acting parallel to the surface, and so is FGX, the x component of the weight. So this is FGX. Now, the weight does not act either parallel or perpendicular to the surface, but we don't really care about this now that we've broken it up into components. And notice now that FGY is opposite of the normal force, and so is perpendicular to the surface. Now, I think it's important that we take a moment to just discuss, because this really should make sense. We should take a moment to discuss the fact that the equation for FGX is equal to FG sine theta. Because what that equation says actually makes a ton of sense. Because according to that equation, the FGX is proportional to the sine of the angle. And as we hopefully know from the equation, the sine of an angle is actually directly proportional to the size of the angle, right? So as the angle increases, the sine of the angle increases. Now, it's not a one-to-one relationship, so it's actually a little sketchy to say they're directly proportional. So let me just write this. As the angle increases, as theta increases, sine theta increases, so FGX increases. And essentially what that means is as the angle increases, more and more of the weight of the object is shifted down the ramp. And I think that makes a ton of sense, particularly when you ask yourself the question, where does the sine of the angle become the biggest? The sine of the angle becomes the biggest when the angle is 90 degrees. And notice essentially what this equation is saying, although it's a little goofy, is that the FGX, the component of the weight shifted down the ramp, is exactly equal to the weight when the angle is 90 degrees. And yeah, that makes sense because this thing is basically in free fall when it's at a 90-degree angle. Additionally, it should also make sense that FGY is the component that has the cosine in the angle, the cosine in the equation, because that equation says FGY is directly proportional to the cosine of the angle. And you should know from the equation that as the angle increases, the cosine of the angle goes down. So that means FGY goes down. And that should make sense because essentially what we're saying here is that when the angle is 0, all of the weight is pushing straight into the surface so that the normal force is equal to the weight. And as you increase the angle, less and less of the weight is pushing into the surface. Particularly makes sense, I think. It particularly makes sense when the angle is 90 degrees because the cosine of 90 is 0. And essentially what that means is that since all of the weight is acting down the ramp, none of it is pushing into the surface. And that makes sense. Notice we can see all of that borne out with that little simulator we were using. And so if we go back to the simulator here, notice this thing can show us the free body diagram. And so I'm going to zoom out here. You can see that as we increase the angle, notice that component here says mg parallel, or in other words, FGX, and this is mg perpendicular, the perpendicular component of the weight, or mg, or FGY, I should say. And so notice as we continue to raise and raise that angle, more and more of the weight is directed down the incline, and less of it is directed into the surface. And that should make sense. Notice we also said before, as the angle increases, the acceleration increases, of course, until we get to 90 degrees. And this thing is basically just in free fall. Because it's in free fall, there basically is no normal force because all the weight is just directed straight down. Now what we're going to do is we are going to take a look at a problem. And in this problem, what we are going to do is we are going to say, for an object at rest on an inclined plane, we want to derive an equation for the coefficient of static friction, mu with the subscript s. And so essentially what we're going to do here is we are going to use the free body diagram, use the equations that we generate from the free body diagram to come up with an equation for the coefficient of static friction. Now, it is definitely true, I think it's fair to say, that most of the problems you'll be looking at for an inclined plane, you're not really going to be too worried about the coefficient of static friction because the objects, if we're talking about static friction, the object's not moving. And that's boring. And so we'll probably mostly be doing problems where the object is in motion. But for now, for this being our first example, I'd like to take a look at an example of a problem where we can just basically put all these equations together and see how they work. And so I'm going to take my inclined plane. I'm going to have a shallow angle here. First, I'm going to draw my free body diagram. So I have my weight vector coming straight down. I have my normal force vector coming up perpendicular to the surface. And I'll have my force of static friction opposing the motion of the object, basically opposing FGX, trying to prevent the object from moving. And so it's important to realize here what we're saying is static friction is acting, so the object is at rest. And it's important to realize here we can, in a component diagram, reimagine this situation so that instead of having the surface tilted, we can sort of rotate the surface in our mind and make it look like this. And so the normal force is going to be acting straight up. FGY is going to be directed opposite of that. We're going to have FGX acting down the ramp. And we're going to have FGY, or excuse me, not FGY, the force of friction, in this case static friction, acting in the opposite direction. And this, it's important to realize, is not to scale. I just want to get a sense of what forces are acting in which directions. Now, it should be noted that the vertical acceleration, if the object is at rest, is 0. And so that means the sum of the forces in the y direction are equal to 0. And what we did when the sum of the forces in the y direction were equal to 0 was we basically said we'll take the forces going up in the positive y direction, the normal force, minus the force going the other way, FGY, we'll set that equal to 0. Now you'll see, I hope in about 1 minute, why it's critical that we do the y direction equation first for an inclined plane, but you definitely want to start with the y direction equation. So we have the normal force is equal to FGY. And so that means the normal force is going to be, well, let's just first move that to the other side. So we have the normal force equals FGY, and then we'll put Fn, the normal force, equals mg cosine theta. And there's our equation for the normal force. The normal force is not equal to the weight because it's not a flat horizontal surface. So I'm going to write here, the normal force is not equal to the weight because it's not a horizontal surface. Now, hopefully you realize why we constantly said that. So there's our equation for the y direction. And for the x direction here, we can say that, well, if the object is at rest, the x direction acceleration is also 0. And so we have in the x direction, the sum of the forces is equal to 0. And so that means the force is going to the right or down the incline, FGX, minus the force going in the opposite direction, the force of static friction, is equal to 0. And so that tells us that FGX, the x component of the weight, or the component of the weight that's parallel to the surface, is equal to the force of static friction. And so what that means, and this will be the last thing I'll do on this slide at least, is that FGX is going to be equal to the coefficient of static friction times the normal force. And I'm going to wrap this up on another slide, but it should be important to note here that now we basically have everything we need to solve for the coefficient of static friction, because I know an equation for FGX, and I know an equation for the normal force now as a result of my y direction equation. That's why you always want to do the y direction equation first. So I'm going to continue this, rewriting it on the next slide here. I have FGX equals the coefficient of static friction times the normal force. Now I know FGX is equal to mg sine theta. That'll be equal to the coefficient times the normal force, and I know the normal force is mg cosine theta. And now hopefully you see where this is going. The first thing I can do is I can realize there is an m on both sides of the equation. They cancel. There is a g on both sides of the equation. They cancel. And so what I'm left over with is sine theta equals the coefficient of static friction times cosine theta. I hope you see where this is going. To solve this for cosine theta, to solve this for the coefficient of static friction, I have to divide both sides by the cosine of theta. So I have sine theta divided by cosine theta. And as I hope you all remember from math, sine theta over cosine theta is the definition of the tangent of an angle. And so our whole big free body diagram work comes down to this nice, neat, tidy little expression. The coefficient of static friction is equal to tan theta. And I'm actually going to show you here how we can interpret this, but I just want to add on to this equation by writing max. And the reason why I'm going to write max there, I can explain to you in words and demonstrate to you by using that simulation. But the point here is the static friction force can change. And because the static friction force can change, then we have to realize that above a certain angle, the object is going to move. But below that angle, the object won't move because the static friction force is just going to change its size. So let's take a look at how that works. So going back to the simulator here, let's just pick a random number here for the coefficient of static friction. Let's pick like 0.3. Let's pick 0.4. And so if we're picking 0.4 for the coefficient of static friction, then let's see what that equation says for us. Well, notice here, if I just raise this to like a modest angle, the object is not moving. Now, it does say there's an acceleration here, but the object is not moving. The coefficient of static friction is 0.4. If I raise it to 13.1, it moves. It doesn't move. If I raise it to 15.8 or 16.2, it doesn't move. But eventually, there's going to be some angle that's reached where the object does begin to move. And so the idea is, when we use this equation, now look, the coefficient of static friction is 0.4. Remember that. The coefficient of static friction is 0.4. And so if I use this equation, the coefficient of static friction equals tan theta max, then that means we can solve for theta max by taking the inverse tangent of the coefficient of static friction. And so that means theta max, in this particular instance, is going to be equal to the inverse tangent of 0.4. And if you take the inverse tangent of 0.4, you get 21.8 degrees. And so essentially, the way that we should interpret this equation and what it really tells you about this angle is that for all angles below 21.8 degrees, you're going to see that the object doesn't move. When we get to 20 degrees, the object doesn't move. When we get to 21 degrees, the object doesn't move. When we get to 21.7 degrees, the object doesn't move. But when we go past 21.8 degrees, the object moves. Now notice it moves with a fairly small acceleration at 21.9 degrees, but it moves. And it's only moving with this acceleration here because we actually made the coefficient of kinetic friction 0. And so what you'd see, and this part I really can't show you, so you're just going to have to imagine it, if we were actually taking a flat surface, like if we had a ramp, but it was a ramp that we could move, and we started gradually lifting that ramp this way, you would see that as we raised the angle, and the angle got larger and larger and larger, once we got to 21.8 degrees, the object would just start to lurch forward. And that's really what we want to get out of it. And so I'd like you to write this down. Note, this equation tells us that the angle the plane is tilted to, which causes the object to lurch forward, is related to the coefficient of static friction by the tangent function. This equation is only true at the angle which causes the block to slide. And so the point is, if we went to an angle that was lower than 21.8 degrees, like let's say we went to 15 degrees, and we just took the tangent of the angle, the tangent of 15 degrees, we would get 0.267. You're not allowed to say, well, because it's not moving here, that's what the coefficient of static friction is, because the coefficient of static friction is one number. It just means that at that angle, the static friction force has not yet reached its maximum value, and so the static friction force is just being canceled out by the FGX, meaning it's not going to accelerate. Take a second to pause this video here and write that down, and when you hit play, we'll move on. All right, and as I mentioned, the static friction problems are kind of boring. Even though that was an interesting little result, that all of that work boils down to just the tangent of the angle is equal to the static coefficient. I think that's pretty cool. But that's really all you can do with that kind of problem. In a static friction environment, you can really use that equation to tell at a given angle, whether or not the object is going to move. But that's about it. And so for the last thing I'd like to do for today, I'd like to move on to a problem where we have some motion, some kinetic friction acting. So it says here a 35 kilogram block sits on an inclined plane, tilted at an angle of 30 degrees. It says here at t equals 0 seconds, the block is released and the object moves down the incline. Find the acceleration of the block if the coefficient of kinetic friction is 0.3. And we could also find the velocity of the block after 3 seconds just for fun. So, of course, the first thing that you're going to want to do here, whenever you're solving any problem like this, is draw the free body diagram. And so we'll start by doing that. And so here we were told that the angle is 30 degrees. And so the first thing we'll do is we'll sketch our ramp. We know the angle here is 30 degrees. Just ignore that line. And we're going to want to draw the forces acting on this block. Well, we're going to have the force of gravity acting straight down. We have our normal force acting up. And we have our force of kinetic friction acting parallel to the ramp like this. Now, as we mentioned, these diagrams are pretty decent. They are the actual diagram that you want to use on the AP test if they ask you to draw the free body diagram. But what I think is sort of limiting about this diagram is it doesn't really give you a whole lot to work with in terms of writing the equations. And so we should write a diagram or draw a diagram with the components as well. And so tilting the surface here, just to imagine it so we don't have to like tilt our necks to look at it, we have FGX acting straight down the ramp. We have the normal force acting straight up. We have the force of kinetic friction. Notice a full vector, so I'm going to draw it as a solid line, acting over to the left. And then we have FGY acting down. And of course, like the last one, this diagram is not to scale. And so, as we did last time, the first thing you want to do here is you want to start with your y direction equation. The sum of the forces in the y direction equals 0. That'll generally always be the case for these kind of problems. And the reason why is because the object is not accelerating this way or this way. It's just sliding down the ramp. And so because the object is just sliding down the ramp, the sum of the forces in the y direction, we're always going to indicate are equal to 0. And so the first thing we have to do here is deal with our y equation. And I think you'll notice a pattern here that our y equation is going to look familiar. So we take the force going up in the y direction, and that would be Fn, and we subtract the force going down, Fgy, and we set that equal to 0. And so what we get, to no surprise, is just that the normal force is equal to Fgy. That's how it works. And so we have that the normal force, Fn, is equal to mg cosine theta. Now, what I notice every year is that a lot of people ignore the advice that I am about to give, and then when it comes to the test, they get in deep trouble. So this would be extremely important advice to listen to. If I were you, I would write this down, even though I'm not going to write it down over here. What I notice is that a lot of people take that equation, because we know the mass, they told us it was a 35 kilogram block, and we know the angle is 30 degrees, and obviously we know g, and they go ahead and they calculate the normal force right here. You should not do that. Do not just calculate the normal force when you get the equation. I'll show you why in a couple of minutes. But the normal force equation is going to look like this, mg cosine theta. And we're just going to leave that. And now the sum of the forces in the x direction, this equation is a little complicated because the object actually is going to be accelerating in the x direction. It started at rest and then it began to move. And so we take ma, and we set it equal to the forces going in the direction of the acceleration. The acceleration is going to be down the ramp in the direction of FGX, so we write FGX, and then minus the force of friction acting up the ramp. And so we're not going to be able to fit all of this work on this slide anyway, so the last thing I'll write on this slide is going to be ma is equal to FGX, which is mg sine theta, and then we'll subtract from that the coefficient of kinetic friction times the normal force. And that's the line I will start with on the next slide, just because I'm running out of room. And so I'll start by writing ma equals mg sine theta minus the coefficient times the normal force. So ma equals mg sine theta minus the coefficient times the normal force. And of course, now I'm just going to go back to show it, the normal force is equal to mg cosine theta. And so we can rewrite this equation as ma equals mg sine theta minus the coefficient of kinetic friction times mg cosine theta. Now, the reason why I told you you should not solve for the normal force is because you don't actually need to solve for the normal force, because there is a mass in this term, a mass in this term, and a mass in this term. And so as it turns out, the mass cancels. And so what we're left with is a, the acceleration, equals g sine theta minus mu g cosine theta. And that is an interesting little result. And the reason why that is an interesting little result is because what it shows is that the acceleration of the object is not dependent on the mass. And that should make sense. It's just like free fall. The mass of an object doesn't affect how much gravity accelerates it, because even if the object was heavier and had more mass, it also would have more inertia. So it would be pulled on by gravity with a larger force, but it would also be harder to move, and those two things cancel each other out. And so the mass doesn't matter. The reason why I say it's a mistake here to solve for the normal force is because people who get comfortable with that end up getting totally thrown off, because since you don't need the mass in this problem, sometimes they don't give it to you. And if they don't give it to you, then you're in real trouble. And so that's an important thing for everybody to pay attention to. So now to solve this for the acceleration, you should notice here, that term has a g and that term has a g. And I don't feel like plugging that in twice, so I'm going to factor out the g from both terms. And that gives me g times sine theta minus mu times cosine theta. And so plugging all that in, I have g, 9.8 meters per second squared, times the sine of 30 degrees minus the coefficient of friction, 0.3, times the cosine of 30 degrees. And when you do that math, sine of 30 is a half. You subtract 0.3 times cosine of 30, and you get 0.24019 and a bunch of decimals. And then when you multiply that by 9.8, you get a equals 2.35 meters per second squared. That's how you solve for the acceleration of an object on an inclined plane. Now, of course, we're not done, because this problem said to solve for the final velocity of the object after 3 seconds. You'll see these on homeworks. I don't really care too much about this because this is like an elementary problem at this point, but let's just do that to finish off this problem here. They told us that the object starts from rest. We now know that the acceleration is 2.35 meters per second squared. And they're asking us what's the speed after 3 seconds. And so, of course, here looking at the equation, or looking at the knowns, we're going to use the equation VF equals V naught plus AT. The V naught is 0. And so we have VF equals AT, and that's going to give us V final equals A, 2.35 meters per second squared, times 3 seconds, and that's going to give us 7.05 meters per second. And sure enough, we should be able to confirm this result using the little simulator that we started out discussing this here in the beginning. And so we'll make the coefficient of static friction 0. It's whatever, we don't need it, we don't know what it is. And we know that the coefficient of kinetic friction here is 0.3. We have to make the static friction coefficient bigger than that, or it's not going to work. So we'll just make that 0.38. 0.3 should work now. Make the angle 30 degrees. And notice, as it says here, the acceleration is 2.35 meters per second squared. It was 2.35388, and so technically to 4 significant figures, it would round to 2.354. Notice it doesn't matter if we increase the mass from 3 to 10, same acceleration. And when we let this thing go for 3 whole seconds, I'm going to try to stop it right at 3 seconds, close enough, you can see that the velocity is 7.033. And so it's about 7 at 3 seconds. And that's the idea. You'll work the free body diagram equations that you derive, and you can solve for whatever needs to be solved for. As we mentioned, all forces problems are exactly the same. You get all the equations based on the free body diagrams. And that's why it's critically important to be able to draw the free body diagrams as well as write them. And that's it for today. Tomorrow, we will use inclined plane and Newton's laws ideas along with friction ideas to solve some more problems dealing with the inclined plane. All right, everybody. Have a good one.